Now, what we've discussed so far essentially paints a picture whereby the main thing associated with the Bold effect is changes in CBF. So CBF is indeed the primary factor associated in the vascular response with the Bold signal. However, there's a very important moderating factor, and that is baseline effects. See, the level of basal CBF plays a very important role in the Bold effect. Let me show what I mean. So this is an experiment by our own Mark Cohen and colleagues. And they did, what they did is they showed, I believe, a visual stimulation to participants under in fact, three different conditions. One is normocapnia, which means participants were just sort of breathing normal concentrations of air. And then they did two conditions: hypercapnia, which means a condition in which participants were breathing more CO2, and hypocapnia, so a condition in which there was less CO2 in what participants were breathing. Now, what is interesting, so what you're seeing here, let's start with the hypercapnia, so the red trace. Now, what you're seeing here is the response to stimulation, right? The magnitude of the response to stimulation. And then where the gray bar starts, this is when participants were administered increased or decreased the CO2. Now, if you increase the CO2, so hypercapnia, in general, the basal cerebral blood flow goes up. In response to inhaling more CO2, there's just a systemic increase in the basal metabolic rate. So if you think of it, there's an increase in CBF notwithstanding any stimulation. The whole system just upregulates CBF. So if you think of it, generally speaking, there will be an increase in oxygenation of the venous side of the blood vessels. So if you now add on top of that some kind of activation because of a sensory stimulation, the Bold response itself, which you see portrayed here, the magnitude of it decreases with respect to before, right? So the magnitude of the response has gone down. As the basal CBF goes up, the magnitude of the Bold effect between rest and task goes down. If you think of it, if you increase the baseline CBF, what are you doing? Well, you're oxygenating more than before the venous side of the blood vessels. If you're oxygenating more the venous side of the blood vessels, it means that protons will resonate more together and will take longer to dephase. For starters, at baseline. If on top of that you also add a task, there is just so much deoxyhemoglobin that can be cleared away by yet another increase in CBF. In other words, the baseline increase in CBF is already kind of washing out some of the deoxyhemoglobin, leaving you with less deoxyhemoglobin to wash out with activation. So the change between off and on, between rest and stimulus, is now smaller in magnitude, because the whole system already got a little more oxygenated to start with. The exact opposite happens with hypocapnia. If you decrease the amount of CO2 in the solution that participants are breathing, the whole CBF, the basal CBF, will go down. As it goes down, veins will have a little more deoxygenated hemoglobin. So if then you have somebody perform a task, the increase in CBF will be even much stronger, leading to a much larger magnitude of Bold effect. And if you look at this graph, you will appreciate that the magnitude of the off versus on at baseline, these two traces, is smaller than the magnitude that you get in hypocapnia. In other words, and whereas in hypercapnia, the magnitude of the response decreases. In other words, the baseline CBF is very important, because if your baseline CBF is very high, you have very little deoxyhemoglobin to wash away to make protons dephase to make protons go together even more. On the other hand, if the baseline CBF is low to start with, then there's all this deoxyhemoglobin that you can wash away with a task, with the increased CBF due to increased neural activity. So the baseline effect is a moderating effect to CBF. And if you just average each of these responses together, you will see in green the middle line is normocapnia. So this is what happens when participants are just breathing standard irregular air. If you have them inhale a solution with less CO2, the bold response will increase a little bit, right? Because there's a greater delta between the baseline amounts of deoxygenated hemoglobin, which has gone up because CBF went down, and the amount of deoxyhemoglobin you get with task, right? There's a greater change. Conversely, under hypercapnia, so when participants are breathing more CO2, the whole system gets upregulated in its basal state. So essentially, you're already washing away more deoxygenated hemoglobin. And so the response to this stimulation right here has a much smaller magnitude and change the shape. So where somebody is in their baseline is a very important factor with how much of a response are you going to get to a visual stimulation or to any kind of stimulation, to any kind of neural activity. If somebody has a low CBF baseline, you will get a gigantic change in the bold effect because there's all this deoxygenated hemoglobin that as neural activity happens, gets washed away and replaced with oxygenated hemoglobin. On the other hand, if the whole system has a high CBF, it means that already the basal state doesn't have that much deoxyhemoglobin to begin with. If it doesn't have that much deoxyhemoglobin to begin with, there's very little that you can wash away and get an increase in the bold signal. So the baseline state of somebody is very important. Now think about this in your research. Are you comparing smokers to non-smokers? Are you comparing very fit people to non-very fit people? Are you comparing patients to non-patients, to healthy volunteers? This already tells you that if there's any difference in the baseline of your participants, it might translate in a difference of the magnitude of the bold effect you might get. So you might think that your patients versus healthy volunteers show a smaller or larger response to some stimulation and think that this is because neurons are responding more or less. But the truth is that it's just because one of your two groups has a higher CBF compared to the other one. And so Fleischer et al., part of the Buxton group, has looked exactly at this. So they looked at two groups of participants who were either at high or low risk of Alzheimer's disease. Neither had expressed yet Alzheimer's disease, but they had risk factors, and they had them do an fMRI experiment. And in the fMRI experiment, the bold response, they found that participants at a low risk of Alzheimer's disease had a greater bold signal compared to participants at a high risk. Now, you might be tempted to say, oh, look, participants at high risk have some kind of dysfunctional part of the brain. Maybe the hippocampus doesn't respond quite as much to my task of interest. Now, it turns out that the whole difference was due to rest CBF. In fact, if you use a different MRI technique known as arterial spin labeling, it's a technique that allows you to measure CBF as opposed to bold. During the active phase, so during the task, the CBF was just about the same in the two groups. So there's no sense in which one of the two groups had a greater response to the task. The difference came entirely from the rest CBF. The low-risk group had a lower CBF baseline. So if you have a lower CBF baseline, it means that when you do respond to something, there's a greater increase and there's a greater bold effect. Whereas the high-risk group had a little higher baseline effect, had a little higher baseline CBF. And so the change from that higher baseline to onset of task isn't as great. And that's exactly what you see on the left side. So there is a difference in bold, but it has nothing to do with how much neurons are activated, and have nothing to do with how big of a CBF response you get during task. The difference is just the baseline effect. So if you are studying any group of patient or two groups that might have differences in baseline resting CBF, you might mistakenly interpret differences in bold as implying differences in neural activity, whereas they might just represent differences in the basal state of the vascular system and the basal state of CBF.